All right. Okay, I think it's working. I hope. Um, so today I'm doing like a short stream. I'm not working on the compiler I was working on the last time because it's like in a messy state right now. So I wanted just to think about it and refactor it a little bit. So I thought about doing something fun, I hope, which is some of the exercises in the Gleam syllabus, which was made public, I think, a couple of days ago. Yeah, so let's do something. I think I'll start with the simple ones and then I'll embarrass myself live trying to do the more difficult ones. Okay, so I was reading this one, yeah, the kindergarten garden. Um, okay, so the problem is this one, we have two strings and they have, oh, hi Ben, hi. Um, so we have two strings and they represent like some pots with plants. And so like you have plants from the first row and the second row, and two by two they belong to one student, and they are Alice, Bob, etc. And yeah, so I think first we need to like parse the string and turn all the letters into plants. So let's do that. So letter to plant, which takes a letter as an input and returns a plant. Easy. So right now I'm not worrying about strange inputs like with letters that do not exist. I think the tests are all with nice inputs, so I'm not worrying about the edge cases. So if we have a V, we return violet, clover, um, what do we have? Radishes and grass. Okay. Um, then what do we want to do? We want to like turn an entire row into from a string to a list of plants, but that is not too hard, I think, because we can just first we need the string module, so string, and we have this useful function which is called toGraphemes, which splits the string into graphemes. So we can do diagram. Oh yeah, it also it's two lines, so we have to split it on the new line. So we can do that. Again, I'm not worrying about strange inputs. I'll just assume it's the right input. So line one and line two, diagram and string dot split on new line. So that's it. Then we are turning each line into a list of plants. So, um, oh yeah, let us sort. Yeah, right. Um, then, yeah, each line into uh, plants. Oh wait, I could also like leave it like this. So we can say split and then we can map over each one. So this dot map. And then here, what do we have? We have a single line. So we have to turn a line into the plants. So we can, again, line to plants. That would be easier to read. So we take a line, which is a string, and we turn it into a list of plants. To do that, we, as I said, split the line into its graphemes. So string dot to graphemes, and then we map over it with the letter to plant. Okay, so line to plants. And now we have a list of plants. Just to make sure that we have something, I'll flat map and return it so we can see if we are on the right path. So, oh wait. I didn't import the list. Uh, do you not use the exorcism CLI? No, I couldn't be bothered trying to install it. I should, but for now I just use the the online editor. Yeah, I should definitely do that. Okay, so yeah, we have something. Okay, yeah, we can parse all the lines. Oh, hi. Um, so wait. Oh, wait. We met at Lambda Days, right? Uh, I'm not sure because I always keep forgetting all the usernames. Yeah, okay. Oh, hi. How are you? Yeah, I was thinking about it the other day. They posted a video on YouTube about Lambda Days, and I was like, oh, I wish I was there. It was so nice. Okay, so let's just keep rolling. Okay, we can turn a line into a list of plants. So let's go back to this. Then we have to split each line into blocks of two plants because um, we have, as you can see in the exercise text, they say that two by two they belong to a particular student. So what we can do is split each line into a block of plants. So we could just list.map and then I think it's called uh, chunks, maybe. Chunk. No, that's not it. Yeah, this one, side chunk. So you give it a list and it returns a list of lists where you have a size and basically it splits into chunks, which is exactly what we want. So list.size chunks from a line and chunks of size, what's the name? Into, okay, into two. So now we can turn each list into our chunks. Um, and last but not least, we can transpose maybe. I think transposing would work here because basically what we have here is like now a list with a list with two lists, which are the lines. So let me just try to display it nicely. So we have a list with two lists, which are the two lines, and each of those has now some chunks. Each chunk belongs to a student. So, for example, here we have violets and radishes, and here we have radishes and what was the G for? Grass. Okay, and grass. So if we say, okay, now let's transpose this, we would have what? These are, no, I don't think that would work. Yeah. Uh, but what can we do here? So we could, oh, zip together those two. Okay, now we have two lists. Yeah, maybe I should have split those into two lines. That would make it easier. So let's assert line one, line two, diagram string.split. And now what are we going to do? We say plants one is line one, line to plants, and list.sized chunks into two. And the same goes for the second line. So line two, yeah, right. So now that we have those two lines, we can zip them together with map2, I think it's called. Yeah, I wrote that, so I should remember it. So basically, map2 takes two lists and it zips them together with a given function. So we can basically join the plants together. We can say let plants equals list dot map2 and it takes the plants1, plants2, and the function is just list.concat. I think it's called concat. I can never remember. Um, oh yeah, there's a concat. No, it's not concat. It's append maybe. Yeah, append. List.append. So we are basically taking these inner blocks two by two. So one from the upper list, one from the lower one, and we are appending them together so that we have the whole block as a single unit and not two distinct blocks. Now we should have a list with 13, no wait, 12 different blocks, which are corresponding to the students. And I don't know what I should do now. Maybe that's it. So let me try this. If that's it, that would be cool. Nope. Size chunk. Oh, size chunk. Okay. What did I write wrong? Plants type. A list of plant. Oh, wait. Maybe I didn't read the. Oh, okay. So we need to get the plans of a particular student. So what we can do now is, for example, get a list of students. So we have const students, and basically it's this thing here as a list. And just let me, yeah, I should use the CLI because working on the online editor is not as as nice as using VS Code. So yeah, but bear with me. So, okay, this is painful. Uh, yeah. So basically, we have all the students. We can zip them, zip. Oh God, the Z is so difficult to pronounce for me. We can zip them together with the plans, and then look up the particular student. Because I think the list module has something like a lookup function, or a key find. Yeah, a key find. So we have a list of pairs. We say we have this desired key and it returns a result. So we can do plants list.zip with students. No, wait, students and plants because the students are the key. So students. Oh, wait, the chat is covering the code. So I should maybe move it around. Bye, Ben. So wait, let me try to move around the chat so it's not in the middle. Where can I put it? Because the last time I realized I didn't put the chat in the so here I think it's even worse because it's covering the maybe I should just remove the chat. Okay, I leave it here. Maybe next time I'll move it around once again. How can I like align it? Uh, Ooh, spoilers. Maybe I should have said it. Spoiler alert. Yeah. Um, okay, the chat is just annoying me, so I just remove it. Yep. Okay, good to go. Okay, so now what can I do? What was I doing? Yeah, I'm zipping the students, so list.zip with plants. And now I'm doing a key find student. So I'm saying, okay, given this list of students and plants, please give me the plants of this student. And that's it. But the problem is that key find returns a result and we want a list. Because if the key is not there, it's going to give us an error. But we can use the result. So uh, import gleam slash result. And here we can say result.unwrap. And if we didn't find it, we just return an empty list. That should do it. So some nice space here. And let me see. Yeah, that works. Great. Um, nice, nice. Okay, so let's submit it. I always like to look into the community solutions just to see if there's something smart that I didn't notice. So yeah, this is basically what I was doing. So size chunks, okay. Oh, so they were turning the students into indices, but I I think I like the key find as well. So I'm not turning my solution into an index one. Um, yeah, so basically they're all the same and they use indices or yeah, they all use indices. Okay, so I can submit it. So mark as complete, confirm. Yep, tell me more. So now what do we have here? We did the kindergarten, and so these are harder, so I'm not doing them now. I'll do them later when I'm tired, so it's going to be a disaster. And let's just go for the, let me see. Yeah, the bird count, which is a learning exercise. So it should be quite easy. Um, and it's a learning exercise to introduce people to recursion. Um, if you didn't know, Gleam is a functional language, so no for loops. And if you want to do some looping, you have to use recursion. So basically, calling the function a bunch of times and bring some state in the recursive calls. And yeah, I'm not a good teacher if you haven't noticed. So um, I'm not reading the introduction because I've already read it. Um, and let's just try to solve the exercise. So the bird count today function should take a list of daily bird counts and return today's count. The list is empty, it should return zero. So it's basically like implementing a list length. So let's do that. Um, and I'm not going to use the standard library functions. That would be indeed quite easy, but let's do it the recursive way. So we can pattern match on the list, a list of days, and what do we have here? So a list can either be empty or have at least an item. So if it has an item, then its size is 1 plus the size of the remaining list. So today of rest, if it has 0 items, it has a size of 0. Um, and this is the recursive function to get the length of the list. But you should take a list of daily bird count and return today's count. But why is the example saying 2 if it's 3? Yeah, I should keep track of this and and make a PR making it the corrections. So yeah, I think that should be that's a mistake in the documentation. So increment day count, what should this do? Um, take a list of daily bird counts and increment today's count by 1. Oh no, wait. How many birds please today? Daily birds count, return to today's count. Oh, yeah, I completely missed the point of this one. So this is a list of days. So the first one is the count of today. So today's count, maybe let's call it that, today's count, and we should return today's count, which is the first one. If it doesn't have if it's an empty list, we return 0. Okay, now we have to increment the day count. So we say case days. If it's an empty list, we should return a list with 1. If it's not an empty list, what do? We say today's count and the rest, and we return a new list with today's count increased, so +1, and the remaining part of the list is left unchanged. So we just say rest of the list. Has day without birds. Okay, so I think now we have to use recursion. So we take a list and we have to guess if it has. We have to tell if it has a day where we didn't see any bird. So yeah, what can we do? So if we find an empty list, so case uh, days, we pattern match on it as usual. And if it is an empty list, what should we return? I think we should return true or false. Maybe let's say true for now and then no, false. We'll see. Um, Otherwise, what can we do? We say today's count and the remaining counts. And we say, so if today's count is 0, then what do? It's um, a day without birds, so we should stop. So we say or, because if or is short-circuiting, so as soon as we have a true value, we stop. So that's okay. Today's count, when today's count is 0, we immediately stop and we don't go in the recursive case. Otherwise, we go into the recursive case and we say has day without birds, the remaining part of the list. Rest. Okay. And if we find the empty list, we say false because there are no days. Uh, so there is no day with no birds because there are no days. Then what's the next? The total number of visiting birds. Okay, so what can we do here? We keep pattern matching on days. Yeah, that's it. It's all pattern matching. So if it's an empty list, we have seen 0 birds. If there is a list with a count and other counts, what do? We take today's count and we sum it with all of the other counts. So we take today's count and we sum it to the total from the remaining days. So one nice way to think about recursive functions is we just assume that the recursive call just does what we want it to do. So we say, okay, total, given a list, returns the sum of the list. And that's it. We just assume that it works. Assuming that it works, we figure out if our implementation is correct. So if this gives us the sum of the remaining part of the list, and we sum it with the first element of the list, then we have the sum of the complete list. So that works as well. And then we have to check that the final case, so the one where we don't go into the recursive case, is also correct. So if this one is correct and this one is correct, assuming that the recursive function does what we expect it to do, then the function as a whole is also correct. And yeah, so if we have an empty list, we have 0. If we have a list with an element and other elements, what do? We take the first element and sum it with the sum of the other elements. And that's it. And now the final one, the number of busy days. So what is a busy day? The number of busy days, 5 or more birds. Okay, so we can still try to do pattern matching. So we pattern match on days. If we have an empty list, we have 0 busy days because there are no days basically. And what do we do here? So if today's count is greater or equal than 5, what do? We return 1 plus the number of busy days in the remaining part of the list. So busy days of rest. So if we have a busy day, so the number of busy days is increased by 1. And then we count the busy days in the remaining part of the list. Otherwise, so in all other cases, so if we have a today's count and we just don't need to pattern match on it, and it's not greater or equal than 5 because we have already checked for that case in this branch, what do here? We just count the busy days in the recursive call. Rest. That's it. So let's see if the tests are good. And yeah, nice. So, um, just to be clear here, what I did do is just implement these functions in the simplest possible way without using other libraries, the standard library, or also without trying to make them more efficient. Um, Once you get into functional programming and doing things recursively, you will find out that um, um, this is not the best way to implement a recursive function, none of these, because these are not tail recursive. It's a kind of optimization that is useful just to make things better because, um, okay, I'm not trying to go deeper into this one. So just know that this is not the maybe the best way, so it's pretty clear and easy to read and really nice, I think, but it can be quite inefficient. Um, the Gleam Exercism track also has a chapter on the kind of optimizations we can do, which is called uh, tail recursive optimization, and you can look into that if you are interested. I really advise everyone to like go and try the Gleam Exercism track. It's really good, and Gleam is like a really fun language. So yeah, you should try it. Um, Great. Show me more concepts. And oh, we've unlocked some new exercises here, which are easy. So let's do those. So I can also say I have completed the whole int part. So Armstrong numbers. An Armstrong number is a number that is the sum of its own digits, each raised to the power of the number of digits. What does that? Oh, okay. I think I get it. So yeah, 9 is an Armstrong number. 10 is not an Armstrong number. Okay. So what we can do here, I think the standard library has something really useful for this one, which is a function that turns an integer into its digits. Let me check for that. Yeah, digits. So we say we want the digits of the number, we say in which base the number is written, and then we get a list of digits. So let's do that. Um, I really like these exercises because it's a nice excuse to like look into the standard library and all the functions and not forget about those. So import gleam slash int and we get the digits of the number, um, let assert. So again, I'm not worrying about the failing case, so I'll just assume that it works, which is the case here because we are always getting a base 10 number. So we get the digits, which we can obtain with int.digits of the number. Okay, so we can then count the number of digits because we need that. So digits count is equal to list.length of digits. And we need to import the length module. So list module, sorry. Okay, so now that we have those, we can check that the number is an Armstrong number. So we need to raise each digit to the power of the number of digits and then sum them together. So we can just, I think there is a, like an exponentiation or something. Uh, Power, maybe? Yeah, power. But the exponent has to be a floating point number. Okay, I don't think that's a problem. We can then uh, turn it back into an integer. So nice thing if you come from other languages like Java, JavaScript, or maybe more OP languages. In Gleam and well, also in a lot of other functional programming languages, strongly typed functional languages, integers and floats are strongly separated. You don't have implicit casts, which can get quite messy. So it's a really nice thing, but sometimes it can make things a bit harder to handle. So you have to explicitly convert from integers to floating point numbers and vice versa. I think that's really nice because you want to be explicit about that and you don't want to get an error somewhere or discover that you've accidentally turned an integer into a floating point and it's just messy. So it's really nice for me that you get like this really strong separation and you have to be really explicit and precise about where you want a floating point number or an integer. So import gleam slash float. At work, I've been working on this TypeScript project, and the number type is giving me a headache because it's like, what's this thing now? It's an integer, it's a floating point number. Should I care? Should I not care? It's just messy. Yeah. So we have the float module, and we can then turn the digits count into a floating point number. So float dot from int, I think there's that. So oh wait, we have an int to float, so we didn't need this one. But I think I'll need the conversion. So yeah, int dot to float. So this turns an integer number, which is the number of digits, into a floating point number, which is needed to do the exponent part. So we can then map over the digits. So we get digits is dot map. And then what are we going to do? We are going to say int dot power. I want to use the labels if we have those. Yeah, power, and we are going to raise each number to the power of the number of digits. And this gives us a list of floating point numbers, which are the exponents. Now we are going to sum those together, which we can do with our reduce. So list.reduce from 0 with float.add. So what is this doing? Basically, the fold function is taking list and taking an initial value, which is 0, and the list elements one by one from left to right, if I recall correctly. And it is adding with the float.add each number to the accumulator and passing it along. So what are we going to do? For example, if we have a list with 1, 2, and 3, and we call the fold, what is going to happen? So it's going to say we get 0, which is the initial accumulator, plus 1, and this is the new accumulator. Then it's going to take the second element and add it together with the accumulator. This again turns into the new accumulator. And then what do? We take the third element and last element and add it again to the accumulator. And yeah, that's it. So we are summing all of those numbers together, and then we need to turn the floating point number back to an integer, compare it with the number, and say if they're equal or not. So what can we call this? Sum of powers. So let's do this, which looks, I think, a bit nicer. And we can turn it into an integer. So let's look into the standard library because I don't remember the name of the function to do that. I think it's called toInt, but I'm not sure. Yeah, I think it's maybe round. So round, what is it going to do? It's going to round the floating point number to the closest integer, and that's just what we want to do. So we say float dot round, we get an integer, and then what do? We can return the result of the comparison. So we say that the number is an Armstrong number if the sum of powers is the same as the number itself, and that should do the trick. So let's see if that works. Oh, wait, okay. This variable is never used because I have a problem here. So oh yeah, I needed to explicitly say which base the number is expressed in, which is base 10. And now we do not have a float dot add. Oh no, because we have a problem here. This dot fold, float add, and digits. It says a result, which is strange. Wait, let me check the float add function. Float to float. So that should be okay. Digits is just a list of digits. So that's, oh, maybe, no, into float should never fail. I don't know what I'm doing wrong. Let me try to do this. So I'll just write it explicitly and plus m and see if we have a slightly more useful error message. Oh, okay, of this type float, but as type int. Oh, okay. So the problem here is that m is an int. Oh, okay, because this one should be a floating point number. So you see, as I was saying before, you have to be really explicit, and the compiler will complain if you mix integers and floating point numbers. And that is nice because I would never have caught that. I would have been wondering, like, why is this an integer? Why are we losing precision, etc.? And instead, it was the compiler which was complaining, which is really nice because we get the error before we even run the code. So this should work now, I hope. No, again, it's not working. So let me try once again to just write this down and um, and sum those together and see what happens. Okay, so the plus expects argument, but the m is a result, which is quite strange, but I think it's because the power function returns a result. So that should be it. Let me check. Yeah, it returns a result. I have no idea why. Oh yeah, okay, because there are cases where it doesn't make sense to get the power. So, what can we do here? Maybe we should just not worry about those pathological cases or filter them out. I think filtering them out. Yeah, I think filtering them out is like the best course of action here. So we can just say we have raised each element to its power. If it was a wrong result, what we can do, I think there is a function in the standard library which allows us to like take a list of results, unwrap all the okay, and drop all the errors, which is what we want here, but I don't remember the name, so I think it's called values. Yeah, right. So if we get a list of results and the example is wrong, so let me just take a screenshot so that I can remember to open a PR to fix that. Yeah, because this one should be an error, not none, because none is of type optional, and here we need a list of results. Um, okay, so going back to the exercise, we import the gleam slash result, so gleam slash result, and we just say result dot values. So result dot values is going to uh, take this list of results because the exponentiation could have failed, and we just say, okay, we drop all the failing cases and we get just the correct cases. And now we can just go back to using the float dot add function here. And now I hope that it's okay. So, largest and last Armstrong number test, which fails, and I have no idea why. I feel like that's because it's a really huge number. And that has some overflow problems, maybe, maybe not, but I'm not sure. So, let's see. Um, okay, I think it's now time to get back to Visual Studio Code. So let me just create a project. Um, Gleam new exercism. Let's open the editor. Okay, so let's see here. The failing test is this one, this huge number, and it should be true. So we should say, yeah, it's the same, but it does not for some reason. So let's check. Let's check that. Um, Huge number. And we say, is Armstrong number this huge number? And we just io.debug it. So we see what happens here. And let me just put some spaces here because it looks nicer. Okay. And move this on top. And we're good to go. So what we can do here is just maybe watch exec Gleam run. Okay, false. It's not an Armstrong number, which is wrong. So let's look into that. So maybe just a bunch of io.debug will do the trick, and we'll hopefully understand what is wrong here. So debug is really useful because you can put it in a pipeline, and it just prints that pipeline step and then returns the result for the following step. So it's really handy when you need to debug things. Okay. Oh, well, maybe that wasn't the best course of action. We have a bunch of okay cases, okay, no error cases, so it's not the exponentiation that is failing. We then take all the values, which is still good, and then we get this huge number, which I guess is not the same. Yeah, we have lost precision somehow. Uh, but why? I really don't want to debug these. So 10, 3, 2. Okay, so it goes to, so the first part is correct up to, oh wait, no, it's 19, 0, 18, 7, 6, 3. Yeah, and here it starts getting different. So I guess there's a problem somewhere, but I have no idea where. So the digits are what we would expect. Yep. 132. Wait, let me just do 219, 763, 992, 565, 095, 973. 971522401. Yeah, so the digits are correct. The number of digits, of course, it's correct because it's a call to list.length, so I don't expect it to be wrong. The power exponentiation part, I think that's where something goes wrong, but I really cannot see what. So I think it's not worth it just going down these. Oh, hi Pietro. Yeah, nice to see you. Um, so yeah, maybe just go to the next exercise. I don't want to be debugging like floating point uh, number shenanigans. So let's just go to the next one. And maybe I'll try to look into it later. Okay, so what's the next exercise in the syllabus, which is an easy exercise. Reverse a string, so that sounds easy. Um, okay, so reverse a string. Um, the easy part, the easy solution would be importing gleam slash string and then just doing string dot reverse value. But I feel like that would be cheating. So let's try to do the slightly dumber and longer solution, which I think is what the exercise was trying to get from us. So what can we do to reverse the string? We split it into its graphemes, we reverse the list, and then we join them together and return the inverted string. How can we do that? So we'll just do this as a like learning exercise. First of all, we do split the string into its graphemes. So value, we can pipe it into the string.toGraphemes function. Then what should we do? We should reverse the list. Again, we could just use the standard library function. I think that's like cheating, so let's implement that ourselves just to learn something. And then what can we do? Once we have reversed the list of graphemes, we can join them together. So it's string.join. And what are we using to join all the characters together? Just the empty string, so that all the characters gets joined together and we get the original string but reversed. So as you can see, Gleam has this nice how do you call it? A pipe operator, which is just used to say, okay, we get this thing and feed it into this function call. The result is fed into this function call, and the result is fed into this function call as its first argument. So it's just like writing string.join uh, reverse string.toGraphemes value and join with this. But it's way, way, way easier to read this one because we are just making a list of all the different steps. And we don't have to like get to the bottom of these function calls to see that we are splitting the string into graphemes, then reversing it, and then joining it. So it's really nice, really useful. How do we reverse a list? So let's write a function to reverse a list. Maybe let's call it reverse list. So this function can work off lists of any kind, so we'll not limit ourselves to a list of strings, but a list of anything. If you have been following the Gleam syllabus, you may have already read about generics. So basically what we are saying is that this list can hold any value of type A. This could be any word, actually, so we could say a list of values. We could say a list of items or anything else. So usually you will see, for example, in the standard library, usually we use single letter types. So a list of A's, a list of B's, etc. And it returns a list, but in reverse order. And how do we reverse a list? Again, I'll just implement the dump, not tail call optimized version. Of course, we can try to be a little bit smarter with the solution, but that's not the point. We're just here to learn something, so let's do things the easy way. An empty list reversed is just the empty list. If we have, however, a list which has a first item and then a remaining piece of the list, what can we do? We can reverse the remaining part of the list. So we say reverse the rest, and we just assume that this work. So we say if this work and the remaining part of the list is actually reversed, then how can we reverse the whole list? And to do that, we can just append the first element to the end, because just imagine you have this list, 1, 2, 3, 4. First is 1 and rest is 2, 3, 4. If we actually get this reversed piece, so if we get a reversed 4, 3, and 2, now how do we get the reverse of this whole list? We just append 1 to the bottom of the list and we get the reversed original list. So we can just say list dot I don't remember the name again, I forgot it. So let's say if we have a way to attach an element to the end of the list, I think it's called append. Yeah, it's called append. So we say list.append, and we append the first element at the end of the list. Um, so this reverses a list. Um, Not the most efficient implementation, but we're not trying to go for efficiency. We are just here to learn something. And that should be it. So let's try to run the tests and see what happens. Okay, so reverse. Oh yeah, I called it reverse list. So reverse list. Let's see. This variable because this field does not exist. The variable is type list A. It doesn't have any fields. What did I do wrong? Oh yeah, I didn't import the list module. So import gleam slash list because I'm using the list.append function. So nice. We have a working exercise. So of course we could have just done this, but I'll just leave a comment here. I'm not taking the easy route of calling string.reverse, but implementing as much possible myself. Just as a reminder for my future self when I get back to this exercise and I see that I've reinvented the wheel. So run the tests again to submit it, and we're good to go. Okay, mark as complete. No, I just want to mark it as complete because it's just not the best solution, I think. We could have just gone for string.reverse. Okay, so we have done that. Armstrong numbers, yeah, that I will have nightmares about that until I managed to find what was wrong with it. So I think we have time for one last exercise, then I will stop the stream. It was around an hour, so I think that's nice. Um, Ooh, I like this one, the collapse conjecture. So it's in the recursive function concept, and so I guess we'll need to use recursion. Um, so start the exercise. What do we have here? So the collapse conjecture says that for any number, uh, for any positive integer, if n is even, we divide it by 2, and if n is odd, we multiply it by 3 and add 1, and sooner or later we'll just get to 1. So let's do that. We have to get the number of steps that we need to get to 1. Um, yeah, so n must be a positive integer. So if it's not a positive integer, we return an error. A nice thing about Gleam is that we do not have exceptions. It's a lot like Rust, I think, in this regard. We deal with errors with the result type. So whenever you have a function that has a return type of result, you know that the function can fail. So it could either produce a resulting value of int, for example, or fail with an error, which in this case is just a single type, which is an error that says non-positive number. So that's pretty self-explanatory where the things could go wrong. So uh, first things first, I think we can check um, for the negative number. So just pattern matching it, case number, in case n is a negative number, so minus. So if n is 0, that's also a problem. So negative or equal to 0, and we just return an error of non-positive number. However, if the number is positive, so we can actually count the number of steps, we just say OK, and then we return the number of steps. So maybe we can use a function to steps, an helper function, number, and number, int, and the steps. So no, wait, I'm not doing the tail recursive optimized function. I'm just doing the easier one, and then we will tail optimize it, do tail call optimization. So this function just returns an integer. So do steps is just an helper function that we assume always receives as input a positive, a non-negative number. So we just return an integer. It cannot fail in this case. And what do we do here? If the number is even, we have to divide it by 2 and count the number of steps to get to 1. If the number is odd, we multiply by 3, add 1, and then go on with the steps. If the number is 1, we are done and we do not have to do any steps, any further steps. So that is our base case in the recursive calls. So if the number is 1, how many steps do we need to get it to 1? 0 steps, because it's already 1. If the number is greater than 1, what are we going to do? We are going to check if the number is even or odd. I don't remember if the standard library has something like is even or is odd. That would be nice. Yeah, it has is even and is odd. So we can say case is even number. So if the number is even, or if the number is odd. So if the number is even, we have to divide it by 2. So we have done one step because it was not 1. It was a number greater than 1. And then we have to call the function again with the number divided by 2. So number divided by 2. If the number is odd, what do we do? Also, we've done another step and we keep doing steps, but this time we are going to multiply the number by 3. So number times 3 plus 1, and that's it. And I think that should do the trick. So let's run the tests. I was not expecting this because what did I do wrong here? Oh, why isn't it working? Number minus or equal. Let's just do this. Case number minus equals 0 if that is true. Oh yeah, right, because I messed up with this arrow. If number minus equals 0. Okay. We could have also pattern matched on is even. Oh yeah, is even must be imported from the int module. So we need to import that. Import gleam/int. And oh wait, run tests and let's see. Great, it's done. So now let's go into maybe tail call optimization. The problem here is that this function uh, is not tail recursive. What do we mean by tail recursive? So a function is in tail call position if it's the last thing we call inside a function. So for example, if we have a function foo, and this function does a bunch of things. So it does like do something, blah blah blah, foo blah blah, and then we call a function here, and we return this. Wait, not a recursive call bar, and this function is in tail call, which means it's the last thing we do before returning from the foo function. And this can be optimized in a way that it doesn't increase the stack size. So we actually don't need to allocate another stack frame when we have a function in tail call position. And yeah, so basically that can help with long running processes and recursive functions. Because imagine you have a function, for example, that calls many other functions. Sometime soon, if you do not have tail call optimization like this, you are going to blow up the stack because the stack frames are going to just keep adding until you exhaust your stack space. So whenever we have a function as the last thing that gets optimized with tail call optimization. Not all languages have tail call optimization, but I think all functional programming languages, or at least pure functional programming languages, have this kind of optimization because, as you might have imagined, we do not have for loops. The only way to do loops is to use recursion. So if we do not have tail call optimization, it would just make our program super inefficient and blow up with big inputs. Okay, so uh, here you can see we can maybe spot a problem because do steps is not in tail call position. It's not easy to see at first glance because it might look like the last thing we do before returning, but that's not actually it because we call do steps and we get its result and then we add it to one. To make it even more clear, we could do this and write it explicitly. So what do? We do steps number divided by 2, and this is the number of steps, and then we return 1 plus steps. So as you can see, do steps is not in tail call position because the last thing we do before returning from our function is summing 1, 2 steps. So a call to do steps is not tail call optimized. So each time we call do steps, it's going to add a stack frame to this stack, and soon it's going to blow up the stack, and we get a stack overflow error. So what we can do here is try to change a little bit our implementation of do steps so that it's actually the last thing we call in each of the branches of the function, and it can get tail call optimized away. So how can we do that? Usually what we do is we add an optional parameter, which is an accumulator, which holds the result of the function. So accumulator, so the result of this function is the number of steps, which is an integer, and the accumulator should be an integer. And when we get to the last step of the recursion, we just return the accumulator, which we assume holds the correct value. So when we get to 1, we just return the accumulator. In the recursive case, what we do is we just call do steps, updating the accumulator and the number, of course. So we update number as we did before, doing number divided by 2, and then we update the accumulator. The accumulator is the number of steps. So here it should be increased by 1 because we just did one step. And the same goes here. So as you can see, it's not that complicated as a transformation. It usually is quite simple if you do not have like hugely complicated recursive functions. It's just a matter of adding an accumulator as one of the arguments of the function call, so that it doesn't blow up the stack, and we can keep calling the function recursively, and at the end just return the accumulator. Now, a problem is right now that we no longer can call do steps with just one argument. We have to provide an initial value for the accumulator. So an initial value for the accumulator is usually what we originally returned in the non-tail call optimized version. Because imagine you are calling do steps with just 1 as the number, so it will immediately return the accumulator. So the correct result in that case would be 0 because we did not do any steps. We already got to 1, so we didn't do any steps. So the correct value for the accumulator as an initial value would be 0. So here, the initial value of the accumulator we can pass to the function is just 0, and that should work all right. So let's try it, and yay, we get the same result. So all the tests are passing, but this time the function is optimized. So I can show you maybe locally in my editor why this matters. So hoping that I can get to an edge case where we get enough steps to blow up the stack. So here we get the steps function, so steps with a number, and yeah, let's try with huge number and see how my computer explodes. Okay, let's try it out. I'm quite scared actually. So why is it not? Oh yeah, I didn't save. Okay, it was quite a small number of steps. Yeah, I don't think it will be easy to find such a big number to get an appropriate number of steps to blow up the stack in the non-tail recursive version. So yeah, I will not try to do that. That would be really boring. So let's submit the exercise, and it will be for the next time when we actually do the the recursive part of the Gleam syllabus. Mark is complete. Yep. Okay, so let's get back to the syllabus and have a look at where we are now. Okay, we did quite a bit of exercises, I think three, maybe four. So I feel like that's a nice point to stop because I only have like the medium and hard exercises left, and I don't want to embarrass myself trying to solve those live. So yeah, thanks for watching the stream and see you next time. Bye bye.